So we talked about the volcanic activity and the connection to a cooling planet. So a minor change in solar activity causes volcanoes to erupt. Well, why is that? Because the sun triggers earthquakes, and that pressure gets transferred around the planet like throwing a stone in a pond. It's like a ripple effect, and that pressure has to transfer all around the planet, and it gets released in volcanoes. All right. So solar flares, coronal holes, and CMEs, coronal mass ejections, they all push energy towards the planet, right, towards our planet in the form of solar wind or cosmic rays, right? So a slight change in that connection causes a ripple effect, which initiates earthquakes, which initiates volcanic activity on this planet. So there's a reason why we always see an increase of volcanic activity during times of solar minimum. Remember, when you study the GISP-2 ice core samples, you can see when there was times of increased volcanic activity, and there's a direct correlation between volcanic activity and a cooling sun. All right, so how does that process work? What does it physically do? So if the sun causes volcanoes to erupt, well then why or how does that cool the planet? So when volcanoes erupt, they release millions of tons of aerosols into the atmosphere. So if these aerosols are, if the eruption is strong enough, if it's powerful enough to break that 50,000 foot threshold, if the aerosols go up to 50,000 feet, that's the threshold. Once they break that threshold, they will remain in the atmosphere for years, decades to come. They get essentially trapped up there. So, well, why is that important? All right, who cares if these aerosols get up there? Well, it is nearly impossible for one water molecule to attach itself to another single water molecule without some kind of binding agent, right? It needs something to attach itself to, and these aerosols act as the perfect binding agent. So once these aerosols break that threshold of 50,000 feet, it now becomes a perfect host for cloud formation. So that's why we talked about earlier in this presentation, early 1800s, why all those paintings were cloudy, dreary skies, because there was millions of tons of aerosols trapped in the atmosphere, which were the hosts for water vapor, which created clouds. So that process is called cloud nucleation. So we are seeing an increase of volcanic activity, right? Well, why is that? Well, because the sun is rapidly cooling. This is Fuego, 2000. This is last summer, Fuego, and I love this picture because it's a great illustration of kind of where we are as a species, just oblivious to the events unfolding around our lives, oblivious.
It's almost arrogant.
Yeah, absolutely. All right, so we're going to talk more about cloud nucleation. So once the clouds form, right? Once we have the aerosols in the atmosphere and then the host for water vapor, well, now we have cosmic rays into the mix. Let's add cosmic rays into the equation. So what are cosmic rays? They are highly charged particles, and they add energy and electricity to the water vapor. I have a slide coming up of what cosmic rays are specifically, but when these cosmic rays come in, they don't come down in single points like bullets coming down from space. They cascade. Whenever they hit the atmosphere, they break into different particles, and they cascade in showers. So when these things pass through, when they zip through clouds, they add energy to the clouds, right? They add electricity to the clouds. And that's why we see rapid cloud formation. That's why we see hurricanes, right, rapidly increase in intensity. That's why hurricane season last year, we saw hurricanes go from tropical storm to a Category 5 in just a couple days, it seemed like. And I predict this summer, we're going to see the same thing. We're going to see storms come out of nowhere. We're going to see, anyway, we'll talk about predictions coming up. So, well, why is that important? So, rapid formation of clouds will further block the sun's diminishing energy. Just think about when you're a kid, you're standing in a field, playing baseball or whatever, and this bright sunny day, and all of a sudden a cloud comes over. Well, you get a little chill, right? Well, this clouds block the sun's energy. It's that simple. Well, when you have a whole planet that's covered in clouds, well, they further block the sun's energy. So there's a connection to clouds and cosmic rays. So let's talk about Edvard Munch's The Scream, right? Painted in 1893. Now, everyone knows this, right? 1893, Scream. Well, 1883, 10 years earlier, Krakatoa erupted in a VEI-6 eruption. So this blood-red sky depicted in this painting can be attributed to Krakatoa. Now, it's through journals, to analyzing Munch's journals and topographical analysis, there's a connection that they realized that this blood-red sky was because Krakatoa erupted 10 years earlier. Just think about if there's a forest fire out on the horizon, and there's always a pretty sunset when there's a forest fire. Well, why is that? Because there's particulates in the atmosphere. It makes a pretty sunset, right? Well, this blood-red sky was because Krakatoa erupted 10 years earlier, and those particulates remained in the atmosphere, causing this beautiful painting. So let's talk about cosmic rays. They're very important. So what are cosmic rays? I'm sure you've heard all the GSM channels talk about cosmic rays. Well, what are they exactly? So there's two kinds of cosmic rays, and they're both identical, but the only distinction is where they come from. Now, there's cosmic rays, which come from our sun, or there's galactic cosmic rays that come from outside of our galaxy. So both cosmic rays do the exact same thing, it's just where they come from. So what are they? They are highly charged particles of protons and atomic nuclei, and they're traveling at near light speed. So our sun is constantly pumping out cosmic rays, right, in all directions, like a sprinkler showering around. Whenever there's coronal holes or coronal mass ejections, it's cosmic rays are flooding out of that area much faster, like opening a faucet, right, flooding out. Whenever a star goes supernova, right, it explodes and particles go in all directions, and these particles will travel until something stops it. So these galactic cosmic rays, well, what stops them? Right? Well, our sun's heliosphere, our sun's magnetic shield, will stop them from, or at least shield them from coming into our solar system. But we'll talk about that in a few slides. So when these cosmic rays hit our upper atmosphere, once they go through our magnetosphere, and when they hit our upper atmosphere, I told you they don't come down in single bullets. They come down in cascading showers. So they break apart, right? These highly charged particles of protons and atomic nuclei, they break apart. What do they break apart into? They cascade the upper atmosphere in showers of gamma rays, X-rays, protons, neutrons, positrons, and electrons, right? They're produced in cascading showers of energy, right? Electricity, again, adding more energy to the clouds, right? So you can even create a cloud chamber in your living room or in your kitchen, right? Just go to YouTube and you can watch kids make it in their house. It's relatively easy. You can watch cosmic rays zip through your living room. So there's a connection to cosmic rays and clouds. So Henrik Svensmark did some research, and there's a video called The Cloud Mystery. If you haven't watched it, you should watch it after this video. He has a profound statement in that video where he says, clouds are not the result of the climate. Rather, the climate is the result of the clouds. That's a profound statement, and it was not welcomed in the global warming community. They laughed at him, right? He was a young guy. They thought it was nonsense. Well, what did he do? He went over to the Large Hadron Collider, LHC, and he proved it. Right? When you have an increase of cosmic rays, you have an increase of low cloud cover. A decrease of cosmic rays, a reduction of clouds. Right? It's that simple. So why is that? Because when the cosmic rays zip through the atmosphere, they excite the atmosphere and they cause the water molecules to attach and form clouds, cloud nucleation. So this is a slide where it ties together the past 3 or 4 slides. So let's look at the top chart here. All right, so now we're back on the solar cycles again. So these are the past Schwab cycles, right? Cycle 24, 23, 22, 21, 2019. So again, counting sunspots. So down here is cosmic rays detection. I don't want to call it a cosmic ray cycle because it's not on a cycle, but it's cosmic ray detection. So there's an inverse relationship to the sunspot observations to cosmic ray observations. Whenever we observe a lot of sunspots, we observe less cosmic rays. Whenever we observe less sunspots, we observe increased cosmic rays. When one is up, one is down. One is up, one is down. There's an inverse relationship. Well, why is that? I'll explain it in a second. So in July 2018, we recorded the most amount of cosmic rays to ever strike this planet. Right here. We're living in a time of cosmic ray maximum. Okay, now why is that? Because whatever happens to the sun happens to our planet. And remember, the sun controls everything. So the sun has a magnetic shield called the heliosphere. And that heliosphere extends out, I believe, past Pluto. It's gigantic. So when the sun cools, well, that heliosphere also shrinks. It collapses down some. It weakens and allows in more galactic cosmic rays. Well, when the sun's heliosphere shrinks, remember, what happens to the sun happens to our planet. When the heliosphere shrinks, our magnetosphere shrinks. So that's why there's an inverse relationship, because the sun is allowing in more galactic cosmic rays, and our planet isn't able to shield us from cosmic rays the way it does with an active sun. So this is another sign that we are indeed entering a period of grand solar minimum, because we are detecting the most amount of cosmic rays ever recorded on this planet.
Yeah, it appears to be going up as well. And you keep mentioning the sun controls everything. And you've said that 3 times in the last 15 minutes. And Mari and I went to a lecture back in 2017 at the Buffalo Astronomy. We were members of their club out there. And the gentleman was showing slides of atmospheric and just different points of changes that recent observations have come back with all the planets in the solar system right now, with temperature change, atmospheric change, cloud change. Different things were happening on different planets. And so that's another part where I like to mention to everyone, if the solar cycles are happening on Earth, they're happening in the entire solar system.
Absolutely.
So
absolutely.
That defeats another debunked part of man-made climate change, because again, it's not just happening on Earth, it's happening in the entire solar system because of what you're saying. The sun controls all.
Yes, sir. Absolutely. It's really that simple. All right, so let's talk about the magnetosphere. I mentioned a few times, so let's really talk about it some more. So our magnetosphere, there's a magnetic shield around our planet. We as a species couldn't survive for 1 second without our magnetosphere. Our magnetosphere blocks solar wind, it blocks cosmic rays the best it can. It blocks everything from space that would immediately kill us. Right? It's our only protection from the dangers of outer space. So that magnetosphere is weakening, and it's weakening exponentially. So we are exiting a time of geomagnetic maximum. All right. During that time, it was estimated that the magnetosphere was weakening at a rate of 0.25% per couple of decades or century. All right. So it was weakening, but only slightly. So in the year 2000, they had to readjust the rate of decline as compared to the 1800s. Now, at that time, we had lost 10% of the magnetosphere, but it was losing at a rate, it was declining at a rate of 5% per century. So in 2010, 10 years later, new data showed that we're losing 5% per decade. In 2015, I couldn't find any data for it. So if you look at that on a chart, it's going straight down. It's weakening exponentially. Well, why is that? Because the sun is rapidly cooling. Because the sun's TSI output is rapidly diminishing. What happens to the sun happens to our planet. So this is an image. It's a video, but this is a still image of our magnetosphere pressure. So it isn't like a brick wall out in space, right? It bends and it flexes like a palm tree flown in the wind, right? It compresses, so when there's a large solar flare, it'll compress and then it'll release and it'll compress and release. So it has some suspension to it. So what makes it strong, what keeps it strong, is when it has a lot of tension on it. So the density changes when it experiences different pressure. So the magnetosphere's strength is not a constant. It fluctuates as it blocks solar wind, right? Again, like a palm tree in a strong wind, it moves back and forth. So the stronger the solar wind, the more tight and compact and strong the magnetosphere becomes, right? This image up here, right? This is where Earth is experiencing a lot of solar wind. So you can see how tight the magnetosphere is. Well, when the sun cools, it doesn't produce as much solar wind, right? And the magnetosphere sort of puffs out. It gets bigger because there's nothing to keep it intact and tight. So this image down here is the magnetosphere kind of puffed out. So sort of the kind of beginner's guide analogy that I've come up with is this analogy with these magic windows in your house. So imagine you have these magic windows in your house and there's a hurricane approaching. So as soon as the wind gets above a certain threshold, your windows automatically turn into hurricane shutters. And they turn into hurricane shutters, and there's hurricane force wind blasting these windows, and they're holding strong. Well, as soon as the hurricane passes, there's no reason to have hurricane shutters, and the windows magically turn back into single pane windows again. Well, they're experiencing a light breeze. Well, what happens when there's no breeze, when it's a dead calm, right? Then your windows turn into a screen mesh, and they puff out, they get weaker. And that's essentially what's happening to the magnetosphere. It's getting weaker. It's exponentially getting weaker and weaker because there's nothing to keep it tight. So our magnetosphere is responsible for more than just blocking solar wind and cosmic rays and shielding our planet. It's also responsible for holding our wind patterns in place, right? Particularly the jet stream here in the United States. The channel of air that flows from west to east across the USA. So as the magnetosphere weakens, it loses its grip on the jet stream. So the jet stream will wander further and further south, as we experienced in January 2019 for that polar vortex that everyone should know about. And if you're unaware of this, in January 2019, USA experienced a polar vortex that brought, I think it was -70-degree temperatures in the Midwest. Chicago, I think, had the coldest temperatures. It was colder in Chicago than it was in the North Pole. Well, why is that? Because the magnetosphere couldn't hold the wind patterns in place, and the jet stream dipped further south, and as it dipped south, it sucked all that cold air with it. But the government and the news will tell you that this cold event happened because of moisture off of the East Coast, because of warming off the East Coast, which is warmth does not equal cold. So again, signs and symptoms are all around you if you know what to look for, right? So just like that one single slide about the Gulf Stream slowing, where it should be on the news for 2 years, this event should be on the news for 2 years, right? Our poles are migrating. We are experiencing a pole shift, or possibly a pole flip. There's still a lot of question about that. I need to do more research, but something to look into. So our magnetosphere, it originates from the center of the Earth, but it comes out of the North Pole and South Pole. I'm sitting here talking with my hands. So it originates from the center of the Earth, but it comes out of the North Pole and the South Pole. Well, when you envision a pole flip, right, you likely envision one pole goes one way, one pole goes the other way, and it's a nice, orderly fashion. You go that way, I go this way. Well, that's not what's happening. What's happening is that the poles are migrating towards each other, right? They're moving closer together. So since the magnetosphere, the magnetic shield, originates from the North Pole and the South Pole, when these poles move together, well, on the back side of the planet, the magnetosphere gets even weaker because the poles are moving towards each other on the other side of the planet. And that's why we have this event here. It's called the South Atlantic Anomaly, because on the other side of the planet, the poles are migrating towards each other. So here in South America, they're experiencing a lot more radiation from the sun.
Yeah.
Because magnetosphere is weaker, particularly weaker in that region. So again, we could spend 2 years on this, but it's 30 seconds. So our thermosphere is also rapidly cooling, another sign that we are entering a grand solar minimum. So our thermosphere is the first, it's the least explored part of our atmosphere. It's important because it's where the sun first interacts with our atmosphere. So over here, right, in this chart, you can see, right, it's rapidly declining. Again, the thermosphere climate index looks identical to the solar cycle charts, or the Schwab cycles. Right? It's not a coincidence. All right, so it's a process to cool the planet. It's not like flipping a switch or just turning down the thermometer. It's a step-by-step process that takes years. Remember, this process started when we had that double peak in 2014. The double peak in solar cycle 24, that second peak when it was stronger than the first, that was the beginning of this descent into this grand solar minimum. So it's a slow process, and no one really believed it was happening because, well, it was still so warm out. But as we're getting further and further into this, we're seeing more and more of these signs and symptoms. And people are beginning to wake up and like, hey, they're saying something is going on. I don't know what it is, but something is, I can't figure it out. So this is the process. So the sun loses power, right? Or it goes into hibernation, what I call it. So we experience an increase of earthquakes, right? Which then we'll see an increase of volcanoes. Once the ash breaks that 50,000-foot threshold, we have more clouds to block the sun, equals further cooling the planet, and winters become longer. So simultaneously, the sun loses power, right? Or it goes into hibernation. So whatever happens to the sun happens to our planet. So when the sun shrinks, when the sun's heliosphere shrinks and cools off, well, our magnetosphere shrinks. So when our shield shrinks, we experience an increase of cosmic rays. So when we have an increase of cosmic rays, you have cloud nucleation, right? An increase of cloud nucleation, which means more clouds to block the sun equals intense weather equals crop failures, right? We're experiencing record crop losses all over the planet, but you likely don't know about it because you don't know where to look. Well, not you, Jake, but listeners.
Right. The gym.
Yeah. So what's next here? So sun loses power, right? Goes into hibernation. What happens? The growth seasons shrink. Now, those of you might not have paid attention, but last winter, right? Winter lasted about a month longer than it should have last winter. And then this winter, we're just exiting. Well, it's still snowing in some places.
Right.
It's May,
right?
It's May 4th. So winter is lasting much longer than it should have. And I guarantee that winter is going to arrive much sooner.
I agree. So, I agree with that statement wholeheartedly.
So our growth seasons are shrinking slightly. And then next year, slightly. And then the year after that, slightly. Our food delivery system is very fragile. Remember, 1816 was known as the year without a summer. So what happens next, right? Severe weather destroys crops. Just follow Ice Age Farmer and his crop loss map, and you can see the crop losses all over the world. It's staggering. So winters become longer. It's a slow process. So food prices increase. Well, what happens after food prices increase? You have food shortages. Well, nothing more important than feeding yourself and your family. Then you have civil unrest. And then the just-in-time food delivery system fails. Well, the mass starvation, mass cold weather deaths, increase in sickness. It's a step-by-step process that we are completely oblivious to.